So the chemistry of weak acids, right? It's why are I mean, you've got three types of acids. You've got alcohols, carboxylic acids, and phenols. They all have these OH groups, and these OH groups they ionize. The H is lost every time, and you form a negative ion. I mean, it's the same dissociation. Just like a weak acid, it's going to be HX, which would be dissociating, ionizing, to produce two ions. Okay, just hold on a second. So it would produce two ions. One would be X minus one, and the other one would be an H plus one ion. Okay, so it's exactly the same type of dissociation. You've got X minus one every time an H plus one ion is produced. So the question is, why are certain acids weak? Why are others relatively and these are all weak acids. Remember, they're all weak acids. We are just relatively comparing them. Which one is stronger compared to them, and which one is the weaker? So we're going to start off with alcohols, and we're going to discuss why alcohols are such. I mean, they are extremely weak acids. So they're not just weak acids. You can't even call them acids. So we're going to start with alcohols. And discuss what's wrong with them. Okay, so why are alcohols such bad acids? Now, here's an alcohol. You've got CH3, CH2, CH2, and let's say there's an OH. Now, this alcohol is going to ionize. It would produce a negative ion, CH3, CH2, CH2, and there's going to be an O minus one ion, and an H plus one ion would be produced. Alcohols have only one acid reaction. I mean, their ionization is even less compared to water. So it's even less compared to water. Now, if you remember, water was also, it did not dissociate that much. So the ions in water were 1 into 10 power minus 7. So this is the concentration of H plus 1 would be even less than 1 into 10 power minus 7 mole per dm cube, which is very, very less. So it hardly ionizes. So the ionization is even weaker, is even less compared to water. And it doesn't really have no typical acidic acid properties. Or behavior. I mean, like, it's not going to change the color of the litmus paper and etc. Like the indicator. I mean, it's hardly you can barely call it an acid, or it barely classifies it as an acid. So it doesn't have any typical acid properties or behavior except for one. And that one is it reacts with very reactive group 1 metals. That's about it. So for example, if you have an alcohol, and that alcohol is methanol. Let's take methanol. If you react it with sodium, the H in the alcohol would be lost, and a salt would be produced. Na plus 1 would take its place, and the H that is dissociated would form an H2 gas molecule. So this is what's going to happen. So the reactions, and the reaction would be a very slow reaction. It's not going to be a very fast reaction. Other acids, they react very vigorously with HCl, for example, with acids. For example, if you take HCl, the reaction with HCl is going to be very vigorous. Like HCl plus Na, the H in the acid is going to be replaced by Na, and it would form NaCl. Plus the H would be displaced and half H2 gas would be produced. But this one is a very slow reaction. So it's an extremely slow reaction. Just a very slight effervescence is seen, slight bubbles are seen. If you do the same reaction with any other acid like HCl, even with a carboxylic acid, the reaction is kind of very vigorous, but not with alcohols. Alcohols are really bad. So it's a very slow reaction, and only very slight effervescence is seen. So the question is, why is it such a bad or terrible acid? Now everything depends on this equation, that an alcohol does not like to lose H plus ions. So we're going to discuss that, what's wrong with alcohols and why don't they like to lose H plus ions. So everything depends on this thing. Everything depends on this X minus 1 ion. And the reason is that this thing over here has a high negative charge density. What it simply means is that the negative charge, -1 charge over here, is so strong that it attracts the H plus 1 back again. This H plus 1 gets attracted back again, and the alcohol does not ionize. There's a strong negative charge, so there's going to be strong attraction because of the high negative charge density. The H plus 1 gets attracted back again, and the molecule over here, it's very hard for it to ionize. Is this point clear?
Yes, sir. Sir, can you explain it again? I didn't understand.
No, I'm just saying the first point is that the reason this molecule over here, the alcohol molecule, does not ionize is that the negative charge over here, everything depends on this negative charge. The negative charge over here is very strong. If it's very strong, what it would do is that it will pull the H plus 1 back again. So the H plus 1, what do acids do? They release an H plus 1. So the alcohol would not be able to release the H plus 1 because this H plus 1 would be very strongly attracted to this O minus 1. So it's not going to break away. It's very hard for it to ionize. Aruba, is this clear?
Yes, sir.
Okay, so it all depends on this high negative charge density, that the negative charge is so strong that it is constantly attracting the H plus 1 back again. It's favoring the reverse reaction. It's very hard for it to go in the forward direction. It's very hard for it to lose that H plus 1. So the question is, why does it have a high negative charge density? It all depends on this carbon chain. This carbon chain has an electron donating effect. What this carbon chain does is, so this carbon chain over here, it's got lots of electrons. Like a carbon chain is full of electrons. Carbon has got 6 electrons. This carbon has 6 electrons as well. This carbon has 6 electrons as well. So you can count the two, and hydrogens have 1 electron each. So you can count, that's 18 plus 2, that's 20, 22, and 25. So they're like 25 electrons in this carbon chain. So the carbon chains are usually very electron rich. So you can think of this oxygen with the negative charge attached to this very electron rich carbon chain. The electrons over here get pushed onto this oxygen, which increases the negative charge at this point. The negative charge over here, it increases because the neighboring electrons also get pushed onto this oxygen atom, which increases the negative charge and which increases the attraction for the H plus 1. Is this point clear?
Yes, sir.
Okay, Lubena, is this clear? Shafak?
Yes.
Yes, sir.
Achha, so the explanation that you're going to write is, and you'll be asked about this, why are alcohols such weak acids? And the explanation for that would be that the alkyl chain, which is the carbon chain, has an electron donating effect. And this is always true for alkyl chains, that any carbon chains are usually non-polar, but carbon chains are full of electrons. Because carbon has 6 electrons, and if you have a big carbon chain, there are lots of electrons in that carbon chain. So if you attach a carbon chain to any group, the electrons on the carbon chain, they kind of get pushed onto that group as well. So if this oxygen was negatively charged, but now the negative charge would be even more stronger, it would have a higher charge density because the electrons from this carbon chain would also be pushed onto this oxygen atom. So alkyl chains always have an electron donating effect, which increases charge density which increases charge density on which increases charge density on this particular ion CH3, CH2, CH2 and O minus 1 ion. And the ion becomes unstable. So making it unstable. What the term unstable over here, what that reflects is that that unstable is something that would change. So it's going to change. It's going to, the negative charge would be so strong that it would immediately attract the H+1 back again to form the alcohol back again. So making it unstable, and so there's going to be strong attraction. So strong attraction for H+1 ions. Which would lead to, which leads to less dissociation. So that's it. That's your explanation for why alkyl chains, why alcohols are kind of really bad acids. ठीक है, is this clear?
Yes, sir. Yes, sir.
So then, if you have a longer alkyl chain, then the effect would be even more stronger. Like it's going to be even weaker. So longer alkyl chains have even more electron donating effect. So they have even more electron donating effect. So the same logic applies. So if you have a longer alkyl chains, it's going to be an even weaker. It's going to be even weaker dissociation or ionization. So that's the reason for this. Now just give me 1 second. I need to change the board. This. That's this one. Now the next thing we're going to talk about carboxylic acids. So we're going to talk about carboxylic acids. These are the ones that are relatively the strongest acids. So we're going to understand the reasons why they are considered to be the strongest out of all these acids. So relatively the strongest acids. What's the reason for that? The reason for that is that first thing, carboxylic acids are your typical acids. I mean, you can call them acids. I mean, they behave as acids in every sense of the word. So they are a typical acid behavior and properties. So if you add a litmus paper, it's going to change color. All the reactions are going to be very similar. So for example, they're going to undergo all reactions. Like if you react a carboxylic acid with sodium metal, it's going to react with it. The H in the carboxylic acid, the OH, is going to be displaced. It would form a salt, and H2 gas would be released. So it's going to react with metals. It's also going to react with your bases, like NaOH. So it would form RCO minus 1, Na plus 1 salt would be produced, and water molecule would be produced. It's also going to react with carbonates, like sodium carbonate, and a salt would be produced, and a water molecule would be produced, and a carbon dioxide gas molecule would also be produced. And at the same time, they would also react with ammonia as well. Acids, when they react with ammonia, same thing happens every time. It's the H that gets replaced. This time, it's going to form an ammonium salt. So all reactions, metal, bases, and carbonates, all of these reactions would take place. And it's going to behave as a complete acid. How does it ionize? A carboxylic acid has RC double bond O and OH. Now it's this H which is highly polar, because all the other H's are not polar. This has a very strong partial positive charge. The reason these molecules, these OH groups, they ionize is that this H over here has a partial positive charge because it's attached to a highly electronegative oxygen. The water molecules around them are polar. So the water molecules have these lone pairs, and the lone pairs are partial negative. The H is partial positive. So the H kind of gets pulled or attracted to the lone pairs on water molecules, and which is why eventually the H kind of breaks away. So every time the same thing would happen, that the water molecule, if you mix them in water, they would ionize. And this ion would be produced. C double bond O and O minus 1 would be produced because the H would go away. So the H plus 1 would be produced. Now I did previously tell you that in water there is no H plus 1. Actually, the H plus 1 would eventually find its way and attach itself to the water molecules. So this this is the simplified version. Just wanted to explain why the H is breaking off in the first place. TK, is this point clear?
Yes.
Yes, sir.
Yes, sir.
So I'm just going to get rid of the water. TK, we don't need to show that. But remember, it's the whole ionization is taking place because of the water that's present. Otherwise, if it was a non-polar solvent, then the H over here might not break off. So it's mainly because there's a polar solvent, which kind of pulls the H away from the carboxylic acid. So now the question is, why is this a strong acid? And the reason for that is, it's again this negative charge over here. I mean, remember the H left its electrons over here. The electrons were left over here, the H left. This has a lesser negative charge density. So the negative charge density on this oxygen is less, which is why it's not really attracting the H plus 1 back again. There is, I mean, it will be attracting. Although it's a weak acid, relatively speaking, it's not going to be attracting the H plus 1 back again. There's going to be less attraction. Right? Is this point clear?
Yes, sir.
Yeah.
Achha, so the question is, why is there lesser attraction? The lesser attraction is, where did the negative charge go? Why is the negative charge not strong enough? The answer is this other oxygen, because what happens is this other oxygen is electronegative. So what it would do is, it would start pulling on the electrons that had accumulated over here. So the end result would be that the electrons are going to get distributed. So the negative charge over here at this particular point would become lesser. It's not going to be pulling on the H plus 1 that strongly, because the negative charge kind of gets spread out to other areas. So at the end of the day, this thing that we call serial bond O and O minus 1, it actually kind of looks more like this. That there's an oxygen and there's an oxygen, and the electrons are kind of distributed. I mean, the double bond over here and the extra electrons that H left over here, they all kind of get mixed. So the electrons are kind of distributed in both places. So it kind of looks like this. And the H plus 1 would therefore not be attracted very strongly to this oxygen, because the negative charge is not concentrated on this oxygen or on that oxygen or at any particular point. So there's going to be lesser attraction. Okay, is this point clear?
Yes, sir.
So we're going to write an explanation for this, which is that that the electronegative oxygen so the electronegative oxygen in C double bond O group has an electron withdrawing effect. And because of that electron withdrawing effect, which decreases negative charge density, on RCOO minus 1 ion, making it stable. And there's going to be less attraction for H plus 1. So there's going to be less attraction for H plus 1 ions, and because there's less attraction for H plus 1 ions, we can say that there's going to be more dissociation. The H plus 1 ions would leave and they would be donated. So hence, there's going to be more dissociation or ionization, and it's going to be relatively speaking, it's going to be a stronger acid compared to alcohols. Okay, so hopefully this point is clear. सही है? Clear है?
Yes, sir.
Yes. And sir, I noted one point. In the alcohols reaction, you made a double arrow, the equilibrium arrow. But in the acids, you didn't, did it? So that also shows the
Which one? This one?
the alcohols reaction.
I mean, you're talking about the reaction with sodium anyway. So these reactions?
Yeah.
These are not.
There's only one single arrow. But in
These,
the alcohol,
you can, that would probably be incorrect. Reactions are not reversible. I mean, these reactions are not reversible. The ionization is reversible. The reactions are not reversible.
okay.
I mean, it's not reversible. Why? Because if your H2 gas escapes, so I mean, that's gone. So you can't really reverse it because the H2 gas would form bubbles and would go away. Is this clear?
Yeah.
Similarly, if carbon dioxide gas is formed, it's going to form bubbles and escape. So you can't really reverse it because the carbon dioxide would be gone before you can even sort of reverse it. So these reactions are not reversible. So anyway, so we have one more left, and that's the phenol thing, which is, I told you, was an intermediate. It was somewhere in the middle. So phenols have intermediate strength as acids. Just hold on 1 second. As a phenols. So phenols have intermediate strength as acids. So इसकी reason ये phenols are the alcohols are the weakest. Then you've got phenols, and then you've got carboxylic acids. So when you move from left to right, the strength of the acids, they continue to increase. So they would increase in this order. These are strong acids. This one is, relatively speaking, weak acid. Alcohols only react with sodium. I mean, your acids can react with three things. They can react with sodium, they can react with bases, NaOH, and they can react with carbonates as well. So your alcohols can only react with sodium. They have no reactions with NaOH. They have no reaction with carbonates, which are also weakly bases. Phenols, on the other hand, react with sodium. They also react with NaOH, but they don't react. They don't have any reaction with carbonates. Carboxylic acids, on the other hand, can have all reactions as acids. I mean, they can have complete reactions as acids. So let's focus on this thing over here. So what are phenols? Now, before discussing what phenols are, phenols are these compounds, the ones with the ring structure in the middle. So they have this benzene structure, and there is NOH. That's what a phenol is, and it's going to ionize. So what it would do is that the H+1 at the end is going to break away. So that H+1 breaks off, O-1 is formed, and it's going to be reversible. Now, before discussing the strength of this acid, we need to discuss what is benzene. I mean, we need a brief introduction of what benzene is. So we need to understand what the structure is, or what the structure looks like. Now, a simplified version of what benzene is, so we're going to focus on benzene for a moment. A simplified version of benzene is, this is known as a Kikulle structure. So it's basically 6 carbon atoms all connected in a cyclic arrangement. So you've got 6 carbon atoms arranged in a cyclic manner, and they have alternating double bonds. So they've got double bonds. Each carbon atom, that fourth bond would be, it's going to form with a hydrogen atom. This one will form with a hydrogen atom as well. This would be bonded to a hydrogen atom as well. So there would be one hydrogen atom attached to each of the carbon atoms. Okay, so that's what a simplified version is. What it really looks like is, for that we need to understand hybridization. Does anyone know what hybridization is? This carbon, like if carbon forms a double bond, what type of hybridization would it do? Like, is it sp3 or sp2 or sp1?
Sp3.
Now you remember, sp3 is when carbon is bonded to 4 atoms. Sp3 is when carbon has 4 electrons, right? If it forms bonds with 4 different atoms, then all the 4 electrons, they kind of bond in 4 different directions. That's a tetrahedral arrangement. And so that's a tetrahedral arrangement, and the 4 single bonds are formed. So this is not 4 single bonds. This is sp2. Okay, so in sp2 what happens is, so this is sp2 hybridization. So what happens in sp2? Now remember, carbon in sp2 hybridization is only bonded to 3 atoms. So it only bonds with 3 atoms. So carbon, remember, has 4 electrons. So if it's bonded to 3 atoms, 1 electron gets attracted to one of the atoms, 1 electron gets attracted to another atom, and 1 electron over here gets attracted to another atom. So they all get attracted to 3 different atoms. Those 3 atoms could be any atom. So there's atom 1 over here pulling an electron, and atom number 2 over here that's pulling another electron, and an atom over here that's pulling the third electron. It's a fan-shaped arrangement. So it's making 3 bonds. You can see over here that this carbon atom is bonded to 3 atoms. So 3 electrons get pulled in different directions. Now the 4th electron, now remember, carbon is in group 4. It has a 4th valence electron. The 4th electron is still in its orbital. No one is kind of attracting or pulling that 4th electron. So that's your unchanged p orbital, which has the 4th electron. And in the beginning, there is no one trying to gain or lose that 4th electron. Okay, so the 4th electron initially is not part of the bonding that's happening, that's going on. Is this clear?
Yes, sir.
Okay. So sp2 hybridization. Carbon makes 3 bonds, fan-shaped. It's going to be trigonal planar.
Sir, are the p orbitals left as lone pairs?
Which one?
The 2 p orbitals that you drew, are they left as lone pairs?
There's a single p orbital. They're not lone pairs. I mean, lone pairs have 2 electrons. This is an incomplete p orbital. Remember, carbon had 4 orbitals. 2s1, the outer shell, 2px1, 2py1, and 2pz1. So it's a half-filled orbital. Like, it's not full. Like, if it was full, then it's a lone pair. But at the moment, what's happening is that 3 of the orbitals get pulled in different directions by different atoms. They bond with them, right? So one orbital gets stretched in this direction because it's attracted to that atom. One orbital gets, so 3 of them, they change their shapes because they kind of, their electrons are getting pulled by different atoms, right? The 4th electron, no one is actually interested in that initially. So it's a half-filled orbital. It needs 1 electron in this orbital as well. So that means this orbital still has room for an electron. So the bonding of this orbital is not yet complete. It needs an electron. So it's going to try and capture an electron from somewhere. Okay, is this point clear?
Yes, sir.
Yes, sir.
So we'll Now, all of them are identical. All of these carbon atoms are kind of exactly identical. So what I'm going to do is I'm just going to sketch this quickly. Each carbon atom is exactly the same. Okay, so all of them are making 3 bonds. And the fourth electron, the p orbital, that, I mean, nothing is happening to it initially. So each carbon atom has this fourth orbital, which isn't really doing much. The other 3 electrons are all engaged in bonding. They're all busy. They've been pulled by 3 different atoms. So all the carbon atoms are kind of identical, right? What happens when you have p orbitals that are in parallel? I suppose.
Pi bonds or sigma, I think. Even, yeah.
I mean, if they're in parallel, remember this p orbital needs an electron, right? So it's going to try and pull the electron from the neighboring p orbital. So it's
Yeah.
going to try and pull electrons from that one, but that one is also empty. So it's going to try and pull electrons from this one. So eventually they would start and merging and overlapping above and below, right? So the orbitals would kind of start. So the orbitals would kind of start merging above and below, and they would form a pi bond. That's where the double bond is coming from. Is this clear?
Yes.
Yes.
Yes, sir.
And these would also overlap, right? Because they're also in parallel. And these would also overlap because these are also in parallel. So there would be 3 pi bonds that would be formed. See, just a second. So there are going to be 3 pi bonds that would be formed. Those are your 3 double bonds. Is this clear?
Yes.
Yeah.
Now the question is, if you focus on one of the p orbitals like this one, why is it overlapping with the p orbital next to it? Why doesn't it overlap with this one? I mean, it's possible that it starts overlapping with this one as well, right? Because all of them are in parallel. So the end result is, instead of getting 3 double bonds, what happens is, okay, they all kind of start overlapping and mixing with each other, and you get an electron ring. That's why there's this circle in the middle over here. Okay, is this clear? So what actually happens is that the double bonds kind of get mixed up. And instead of getting delocalized electron or pi electron cloud over here or over here or over here, you get a pi electron cloud on the entire structure. Okay, so all the 6p orbitals, they kind of get mixed up, and you get electron cloud on top and below everywhere. Okay, ये सारा clear है? Assalamu alaikum.
Yes.
Okay. Yeah.
चलो ठीक है, we'll continue with this. Next class में फिर continue करते हैं. So I'll teach this again. ठीक है, we'll do the, and then we'll discuss about the acid strength as well. चलिए, okay everyone.
Yes.
Take care. Allah Hafiz. चलिए जी, just a second.